Today I'm going to continue the examples we started on Tuesday, and then I'm going to teach two more topics relatively quick. I don't want to go into details of these two topics. They can be very subtle, but I want to give you the basic idea. And for each of them, I want to do one example. Both of them I'm going to teach in the context of the example on capacitors. And once we are done with this, we are basically done with the class. Okay, with this course, we've finished chapter 4. And starting chapter 5, it's magnetostatics, different topics, and that's going to be part of the course next semester. Okay, so the plan for Tuesday is that we will have a quiz on Tuesday next week. We will have a quiz on Tuesday, and the rest of the class, I'm going to give you the solution for the same quiz that we did. So hopefully that's good for you for grading on Critic and for preparation for the final exam. And if we have more time, I'm going to do the solution of the midterm on that day. Okay, if we didn't get the chance to do that on Tuesday, I'm going to email you the solution for the midterm question. Sounds good? Okay, so let me go grab my notes and then we can start teaching. Okay, any questions from the topics we discussed on Tuesday? You guys are pretty quiet on Tuesday, and I guess for it's rare that class goes faster than what I planned, but Tuesday went by pretty fast. Okay, so if there's no question, I'm gonna start this example. This is example 4.7 of the textbook. So just to repeat and remind you what we've been doing. What's happening here is that we have a uniform electric field. And then we have a spherical dielectric. We put the dielectric material inside that electric field, and it's going to bend field lines a little bit, okay, because of all the charges that get induced on the surface. And maybe inside, but we will find that there is no charge inside the dielectric. So what's going to happen is that the electric field changes outside and inside as well. The question is asking what is the electric field inside? And I draw the field lines here, and surprisingly you will find that the electric field inside the dielectric is going to be uniform, okay, but it's going to have a different strength from what's happening outside. Okay, so for problems like this, the general way you should think about this is basically we want to solve the Laplace's equation. And for the Laplace's equation, we used to look at the equation. So we are looking for a solution that satisfies the Laplace's equation as well as all the boundary conditions. So what we started on this one is we followed the topic of separation of variables that we started in chapter 3. So we looked at that, and we looked at the solutions that have the form of two functions multiplied by each other. One is only function of the radius, the other one is function of theta. Okay, so that was the general way we looked at the potential function inside and outside. And once we have that function, we should look at the boundary condition and find the solutions that satisfies all the boundary conditions. We listed the boundary conditions for this problem. So there are 3 boundary conditions. One of them, what's happening at infinity, where we are way far away from this spherical conductor. The point was that the potential should be exactly the potential created by a uniform electric field. And then we look at the boundary on the surface of the dielectric. There are 2 boundary conditions. One of them is the continuity of the electric potential, and the other one is discontinuity of the electric field. Okay, so I'm going to go over them one by one, and I want to write them on the board and then we continue. So the general solution following separation of variable for such problem, so V, the potential as a function of the radius and theta. Here we have symmetry in the azimuthal direction, so there's no dependence on phi. The potential is going to be only function of r and theta. Okay, so the general solution following the discussion in chapter 3 is a linear combination of functions that have the shape of AL r to the L plus BL plus 1, BL r to the L plus 1 times PL cosine of theta. Okay, so this is the general solution for the case of in a spherical coordinate where we have azimuthal symmetry. And then we look at the boundary condition. The first one, let's look at the continuity of the electric field on the surface of the sphere. Okay, so in order to look at that, I'm going to separate the function that describes the potential outside and the function that describes the potential inside. So we have two functions, V in of r and theta. This is the potential inside the sphere, inside the dielectric, and then V out, which is again function of r and theta, is the potential outside the dielectric. Okay.
Professor, for both, for potential in what's the first symbol?
V in the first symbol is r.
Oh, okay. Thank you.
Are functions of r and theta. Okay. So so then boundary conditions, I'm going to write them at this corner. Number one, continuity of the potential on the boundary. That means V in at the R on the surface of the boundary, which is capital R, and theta should be equal to V out R and theta. Okay. The second boundary condition was the discontinuity of the electric field. So on Tuesday, we discussed that on the surface, so on any boundary, electric field can be discontinuous if you have any surface charge. In terms of the dielectric materials, if you have something that dielectric constant is different on both sides, even if you do not have free surface charge density on the boundary, the electric field can be discontinuous, and that's because of the accumulation of bond charges on the surface. Okay, so this is one of those cases. There is no free charge density on the surface of this dielectric. The dielectric was neutral when we put it. But because of the polarization and because we have different dielectric constants across this boundary condition, okay, across this boundary, the vertical component, the normal component of the electric field to the surface can be discontinuous. Okay, so to capture that epsilon, okay, which is the dielectric permittivity of the sphere times the normal component of the electric field that I'm going to write in terms of dV in over dr should be equal to epsilon naught dV out dr. Okay, and the electric field is discontinuous because the epsilon and epsilon naught are different. Okay, if you have the same material on both sides of the boundary, there will not be any discontinuity unless there is free charge on the surface. Sounds good? So this is the boundary condition number 2. And number 3, the potential where we are far from this sphere, that means the V out should behave exactly like this. This is the potential of the uniform electric field. Okay, so when we are far away, by the way, this has to be correct at R equals capital R at R equals capital R, okay? And then V out at R goes to infinity, and theta should be negative E naught R cosine theta. Okay, and obviously here the assumption is that the electric field, the uniform electric field is in the Z direction, okay? And Z here is going to be R cosine theta. That's how you convert Z to polar coordinates. Sounds good? So is everybody happy with the way we develop the boundary conditions and the potential here? That's important. For problems like this, it's always important for you to analyze the geometry, see what you have, and analyze the boundary condition very carefully. Once you have the boundary conditions and once you know the general solution, the rest is going to be just mathematics. If you set these things up correctly, it's going to be a lot easier for you to continue. If you do a mistake at the beginning to pinpoint what boundary conditions you have, you're going to carry that mistakes all the way to the end of the problem. Okay, so remember, always focus on what geometry you have, what boundary conditions you have, and the rest is going to be easier for you. Sounds good? Any question? All right, so let's now move on. So let's see what kind of form the V in and what kind of form the V out can have. This is the general solution. Okay, V in is the part of the potential that is around R equals 0. The origin is here, and V in describes the potential inside that sphere. Now, if you look at that, and if you look at this general solution, the second term in the R function, which is BL over R to the L plus 1, we need to get rid of that for the V in. Why? Because if we include that at R equals 0, this term is going to blow up, and we don't want that, okay? So for V in, which is potential inside, I would write the general form in terms of only the first term and the Legendre polynomials for the polar coordinates. So this is L from 0 to infinity, AL, R to the L, PL, cosine theta. Okay, and for V out, the same argument, but the other way around. If we include the first term at R goes to infinity, that blows off. We don't want that. So V out, let me give it a little more space here. V out of R and theta is sigma L from 0 to infinity. We only have the second term, R to the L plus 1 times PL cosine theta. Okay, so this is what we have for V in and V out. These are simplified relative to the general solution only by considering the behavior at R goes to 0 and the behavior at R goes to infinity. Okay, so now we should take this and this boundary condition, and we want to narrow down what options on AL and BLs we can have. Okay, so the rest of the problem is identifying the ALs and BLs. Okay, now what I want to do is that I want to look at this boundary condition. Let's look at the number 1. This says that V in and V out should be exactly the same on the surface of the boundary where R, radius equals capital R, the radius of the sphere. Okay, so from that boundary condition, we can say oh, by the way, for V out, we get rid of all the R to the power of L or the ALs, except for one of them, okay, that I forgot, for R to the power of 1, where L, where L equals 1, we need to keep that because we eventually want to match that with this boundary condition, okay? So we get rid of all these terms for all the ALs except one of them, and that is the one that has r to the power of 1 because we need that here. So I keep that negative E naught r cosine theta. Okay, so I just add that manually here because eventually I need that. Sounds good. So we go to number 1 and we just write everything in terms of a small r being equal to capital R. Okay, so on one hand, I'm going to write B in, which is the sigma from 0 to infinity AL R to the L PL cosine theta, and on the other hand, I have sigma L from 0 to infinity BL R to the L plus 1 PL cosine theta minus E naught R cosine theta. Okay. So now if you look at this, we can relate AL and BL to each other, okay, through this equation, okay. So for the case that R is equal to capital R, by the way, this is not capital R. For the case that L equals 1, we have this term as well, and if we write equation for that, only for case that L equals 1, what we get is that A1R, which is this term, okay, A1, R1 basically should be equal to B1 divided by R2 minus A0R, okay? And if you remember, the P1 of cosine theta is cosine theta, okay? So for L equals 1, cosine theta is canceled out with P1 cosine theta, P1 cosine theta. And what we get from that, there's a relationship between A1, B1, and E0R. Okay, so that is correct for the case that L is equal to 1. Okay, for other values of L, okay, these two sigma should match each other. So for L, other values, L not equal to 1, we get an equation that says AL R to the L, which is a term here, should be equal to BL to R over L plus 1. Okay. So in order to match these, we need to make sure that for L equals 1, the relationship between A1 and B1 is like this. And for the rest, we need to make sure that all the AL values match BL values based on this, okay? So this is the two conditions that we get for A1, B1, and the rest of the AL values, okay? So this is from boundary condition number 1. If we look at the boundary condition number 2, that's gonna give us another set of equations very similar to this, but a bit different in a way that those equations combined with this one is gonna give us a system of equation, then we can solve it for A1, B1, and the rest of AL, BL, okay? So now I'm gonna look at the second boundary equation, boundary condition, and I want to erase this one, write that boundary condition, and come up with one more set of equations here, okay? So now I'm going to look at the boundary condition number 2 and what we get from that. So technically, the same thing, if we take the derivative with respect to R, from the top one, we get L times r to the power of L minus 1. And from the second term, from this one here, we get negative L plus 1 BL over L plus 2 here. And on this term, we just get rid of r, we get E naught cosine theta. Let's write that down and see what kind of equation we get. Okay. So I'm going to use epsilon r, which is epsilon over epsilon naught. Okay, so here I want to write it that epsilon r is epsilon over epsilon naught. And the derivative of the first term, V in with respect to r, gives me sigma over L from 0 to infinity, L times AL r times L minus 1. So if you look at this term, this is basically the derivative of this. Okay, so L comes down here, AL times r to the power of L minus 1. But because we are looking at this derivative exactly at r equals capital R, I write it capital R here. Okay, so this is the derivative of the V in with respect to r. And then we have PL cosine theta here. This is one side of the equation. Now, if you look at this, the other side of the equation, that should be equal to sigma L from 0 to infinity. And what we get here is negative L plus 1. Negative L plus 1 because r to the L plus 1 is in the denominator. I'm taking derivative of this, so I get a term negative L plus 1 times BL divided by r to the L plus 2. And L plus 2 is for the same reason I'm taking the derivative of this. Times PL cosine theta. Okay, and now I want to get rid of these three lines here so that I have a bit of more space. And then we have this term as well. We are taking the derivative with respect to r. That gives us a constant term E cos theta. Okay, so I'm writing 1 here just to give you this set of equations from number 1. And now the same thing goes here. We can look at L equals 1 and come up with a relationship that tells us what should be the relationship between A1, B1, P1 cosine theta cancels out on every term because that's just cosine theta, so we can get rid of that. So for L equals 1, we get another equation. I want to write that here. Okay. And here we get for L equals 1, get A1 equals negative 2B1 divided by R3 minus E naught. Okay, so that is when you put L equals 1. The PL term cancels out with this and with cosine theta. Because L is 1, this term disappears, okay, and this term, this L just becomes 1. So from the left-hand side of the equation, you just get A1. And then, by the way, we have epsilon r here as well. We just get epsilon r A1, and from the right-hand side of the equation, we get E naught from here, which is negative E naught here. Negative of L plus 1, we get 2 here, B1 divided by R3. Okay, so that's going to be the relationship between A1 and B1 derived from boundary condition number 2. Okay, now if we look at other terms in this summation, we can come up with another relationship for all other AL values. This term doesn't count because we already counted that in case that L is 1. So there's this term, these two summations are going to give me relationship between AL and BL in terms of R, and that is epsilon R, which is this, times L AL R to the L minus 1. Okay, so the whole terms here that you see is basically the terms here, and that is equal to negative of, now we should write the terms here, okay, which is negative of L plus 1 BL over R to the L plus 2. Okay, and again, this follows this. This is for L equals 1. This is for the rest of L values. Okay, so we looked at the first two boundary conditions, okay, and come up with an equations for AL, BL, A1, B1 separate, and again, another set of equations for A1, B1, AL, BL values. Okay, now if you look at these two equations, this one, let me put them in different color. This one and this one combined, these two in red box, they're gonna give us a system of two equations, and we have two unknowns. The two unknowns are A1 and B1, okay? And also, if you look at these two, this one and this one combined give me two equations for two unknowns. What are the two unknowns? AL and BL values. Okay, so from this, we can solve for A1, B1, and AL, BL. Okay, and that's what's interesting is that you will see the only way you can satisfy this green box and this green box combined is setting AL and BL values equal to 0. Okay, so the way this is set up, you can write AL in terms of BL divided by R to the power of 2L plus 1, and you sub it back here. There's no way you can find any solution for AL and BL except all the AL values. Okay, so from these two, all the AL should be equal to BL, and that should be 0. And that means making the both sides of these equations 0. Okay, and that's interesting because over all this summation, it looks like the all AL values are going to be 0, and eventually the potential is not going to have the form of a linear combination of infinite number of solutions. It's just going to be one solution, and that is for the case that L is 1, and we only have A1 and B1 in this general solution. Okay, so that's for all the values except 1, and if you look at this one, the red boxes, from that one we can actually find what is A1 and what is B1, and I can give you the solution that A1 should be negative of 3 divided by epsilon R plus 2 times A0, and B1 is epsilon R minus 1 by epsilon R plus 2 times R3E0. Okay, so these two are the only terms in the V in and V out linear combination that matter. Okay, and that means we don't really need to include all these Legendre polynomials of PL because only L equals 1 matters, and that is only the cosine of theta. Okay, so if we take these two and sub it back here, I want to, you know what, I'm going to get rid of this diagram now. Okay, so with only these two values V in is going to be equal A1, which is this, times r to the power of 1 times cosine of theta, okay? And that is negative 3 by epsilon r plus 2 times E naught times r cosine theta, okay? So this is the potential inside, okay? And that only have, here we only have one term, okay? We don't have the summation anymore. And the potential outside is this B1, which is epsilon r minus 1, epsilon r plus 2, times R3 divided by R2 times E naught minus E naught R cosine theta, okay? And that is the term V out. I'm gonna put them in box so that they stand out in the busy whiteboard today. Sounds good? So what we did was we basically started from very general solution here on the top. We started from this. We narrowed down the options a little bit. We came up with a bit more simple solution in a way that we got rid of one term for this one and the other term for the V out, okay? And I added this manually because I knew that V out should behave like this when R goes to infinity, okay? So again, starting from this, and then I looked at the boundary condition number 3 is already considered in the way we wrote V out. Then I focused on boundary condition number 1. I came up with these two sets of equation, okay? And then I look at boundary number 2, I came up with these two sets of equation, okay? The top ones in red box are actually equations for A1 and B1, okay? We can solve that. 2 equations, 2 unknowns, these are the solutions we get. From the green box, we can solve for all AL values and all BL values except for L equals 1, okay? And the obvious solution for that was AL equals BL equals to 0, okay? And that's nice because if all of them are 0, we don't really need, the solution is not in the form of an infinite number of, in the form of a linear combination of infinite number of solutions. We get just one term here that corresponds to L equals 1. And this tells me the potential inside. And the second term tells me the potential outside. So B1 subbed here. That's it. Of course, we always carry this because that's the term we added manually. Sounds good? Any question?
Where do we count for the first condition? I mean the third?
The third condition, when I put that here manually, I already meet the last condition. Because
Okay,
if you look at this, we have all the r to the power of L plus 1 values at r goes to infinity. The first term, and actually all the terms in this summation, they disappear, and we will end up having this term.
Okay, thank you.
And that matches this one. And just, I'm going to say that I'm putting number I here so that you know these two equations are from boundary condition number 1. And I'm going to put 2 here so that you know these two equations come from boundary condition number 2. How do you feel about this? Does it look complicated? Mathematically, I believe it looks complicated. If you look at this whiteboard in one snapshot, you're going to say, oh my God. But I'm telling you, this is one of those things, if you do it yourself a couple of times, not once, but a couple of times, then you will find, just one minute, okay? And you will find the concept is not that complicated, the concept is nice, And the mathematics, if you look at every single step, is not that bad. Okay, even though it has many, many steps, every single step is not too bad. Just do that, practice that number of times, and then it's gonna be fine. Okay. Anyways, so today is one of those days. My daughter is having her school online in the next room, and instead of listening and focusing, she did this painting and brought for me. so, you know what I'm thinking? I hope you guys are not doing any drawing and painting, and you guys are focused on this. Okay. Any question on this?
Yeah, I have a couple of questions. How you ended up eliminating the denominator on B or B in, and how you kept it on B out?
Okay. So for V in, I eliminated this term manually. Why? Because V in includes the area that R goes to 0. And in that limit, the second term, BL term, is going to blow up. I don't want that. I don't want potential go to infinity inside my dielectric. So I just got rid of this one at the very first step when I was rewriting it up here. Now, if you look at V out, you see I eliminated this term, all the AL values here, technically except the one that has R to the power of 1, and I only kept that one. And for the same reason, for R goes to infinity, I don't want potential blow up unless it follows this term, which is E naught R cosine theta.
Okay, I get it now. I get it now.
Okay, good. More question? Nice. Okay, so this is one of those kind of problems I really want you to look at the example, probably watching my video again, reading the textbook, have a couple of pieces of papers next to yourself, write down every single step and try to make sense of every single step. Once you do that a couple of times, I would say maybe even more, several times, then it really clicks and you really feel what the method is. Sounds good. So I'm going to do one very last step. And in fact, if you remember, the question was, what is the electric field inside the dielectric sphere? So what we found here is the potential. V in has the same form of this. And if you want to find electric field from electric potential, that's one derivative, right? So this potential R cosine theta in polar coordinates, you know that's always equal to Z, okay? So potential in terms of the Cartesian coordinates, in terms of the Z, has even more simple form, and that is negative 3 E naught over epsilon R plus 2 times Z, okay? And if you want to find the electric field, is negative of the gradient of the potential. Potential is only dependent on Z. So in this case, the electric field is negative of dV dZ times Z hat, and that is negative 3 E naught over epsilon R plus 2 times Z hat. Okay, now if you look at this, we can do a quick consistency check. Okay, so what if the dielectric that I'm putting in hypothetically has the same dielectric constant as vacuum, which makes epsilon R being equal to 1? If I do that, that's technically that dielectric is nothing, right? You can, in a way, you can imagine you are putting one vacuum sphere over there. Epsilon R becomes 1, 1 plus 1 is 1 plus 2 is 3, cancels out the 3. So what we get at the end is just epsilon naught times Z, which is the uniform electric field we had before. By the way, there's a negative here, there's a negative here, so the last term should be positive. Okay, and now if you imagine that you put some dielectric sphere which has very, very strong epsilon, okay, permittivity is too high, the stronger it is, right, the bigger the denominator, so the electric field that is penetrating inside the dielectric becomes weaker and weaker, okay? And if you choose something that has extremely high epsilon, and that is technically a conductors. Conductors in a way are similar to conductors, you can compare them with dielectrics with super high epsilon, okay? And then the denominator becomes super big, the whole thing here kind of vanishes. And that's when, if you put a conducting sphere, you do not get actually any electric field inside the conductor. Sounds good? Any question on this? So if there's no question, I'm going to actually move on to the next two topics, which are relatively quick, okay? I'm going to give you a heads up that both of the topics I'm going to discuss, they can be subtle, okay, but I'm not going to go into much details of them because these are both kind of things that conceptually can be complicated, but at this point, I don't want to make it complicated for you guys. I just want to have a nice overview of energy in dielectric. So specifically, I want you to be familiar with the equation, how you calculate electrostatic energy in systems that you have dielectrics and dielectrics are present. And then I want to do basically one sample that we calculate the force on dielectrics. The idea is that dielectrics, because they get polarized, okay, if you put them in electric field, they can feel some forces, okay? And what I want to do is that I want to look at the case that we have a parallel plate capacitor. We put a dielectric slab into the capacitor, and then we try to slide that dielectric slab out of the capacitor. You can imagine if you're taking that out, you may experience some force, okay? I want to look at the energy work and energy theorem in a way to find what force we have. Okay, so let's move on and let's do them on the board so that you have a better idea. So shall I erase these things? No question? Okay. Cool. All right, so let's look at one capacitor. And imagine we charge the capacitor to, in a way, we connect it to a battery with potential of V. So we end up having some electric field inside this, okay, because you have accumulation of charges on the positive and negative side. And energy of the capacitor, we calculated that it's 1/2 CV squared. Okay, so V is the potential across the two plates, C is the capacitance, and W is the energy we have. Electric energy is stored in this capacitor. Okay, now think about this. Imagine we put a dielectric slab inside the capacitor, okay? So when we fill it out with dielectric slab, what happens is that the capacitance we calculated, it changes, right? If you follow the discussion we had on Tuesday, the capacitance with dielectric, okay, is equal to epsilon divided by epsilon naught times the capacitance in case we have vacuum, okay, in between the plates, okay. So this tells us that always if you put dielectric, we get greater capacitance, okay. So if the capacitance is increasing and if we are charging up the capacitor to the same potential, what happens is that we get energy stored in the capacitor with dielectric, which is going to be greater than the capacitor with vacuum. Okay, and the relationship kind of simple, follows the same thing. This is going to be equal to vacuum capacitance times epsilon over epsilon 0. Okay, and this ratio is always greater than 1. Okay, so now we already know that the energy in the capacitor is increasing. Okay, in other ways, if you think about this, the potential difference is the same, meaning that the electric field between the two plates must be the same, right? Because we connected to the same battery, same potential difference, same gap between the plates. So at the end, we have the same electric field. Okay, now the paradox is that if we go back to our definition in chapter 2, how to calculate electrostatic energy, we had the equation of epsilon by 2, electric field to the power of 2 times theta, and that's an integral that runs over the volume over the whole space. Okay, so if you look at the electrostatic energy through this equation, you're going to get the same energy for two capacitors with dielectric and without dielectric. Okay, but if you follow the equations for capacitor, you will see easily that the dielectric capacitor carries more energy. So what's happening is that this equation is developed for the case that we do not have any dielectric, okay? And if we include dielectric, this equation needs to be rewritten, and W becomes epsilon naught by 2 divided by, so integral of e to theta. How much is increasing is a factor of epsilon over epsilon naught, or the combination, I'm going to say dielectric constant E naught. So everything is multiplied by ER, okay? And another way to write this is actually epsilon naught over 2. The integral of, instead of taking the integral of e to the power of 2, you can take the integral of d dot e. D is the dielectric, is the electric displacement, which is basically epsilon r times electric. Epsilon times electric field times theta. Okay, so long story short, the message here is that if you have any dielectric involved in the problem, you cannot simply look at the integral of E squared theta. That only considers part of the electrostatic energy stored in the system. If you have dielectric, what you want to follow is the integral of d dot E. You're going to find energy which is slightly greater than what you would have found through this. What's happening here conceptually is this. Even though in a system like this you are getting the same electric energy, the effect of dielectric is that you put dielectric there. As you charge up the capacitor, you are actually polarizing the dielectric a little bit as well. Okay, so as you are polarizing dielectric, you can imagine you are adding some more work, and you're also bringing more charge on the two plates of the capacitor in order to create the same potential difference and the same electric field. Okay, so because of that, if you compare two systems similar with and without dielectric, the one with dielectric always takes more energy to set up, okay? It takes more energy to bring all charges to create the same field, and that is because of the effect of the polarization in the dielectric material. Sounds good? There is one example in the book. I'm going to skip that example because that goes into details of how things get polarized and stretching molecules and so on. Okay, I don't want to make you too confused by all details, but I want you to really understand the example of a capacitor well, and you understand what kind of energy you can calculate without dielectric and what energy you can calculate with dielectric. And I want you to be able to connect that to the equations of how we can integrate the electrostatic field over the space to find the energy. Sounds good? Any question? No? You guys are being very quiet this week. All right, so if there's no question, I'm gonna move on, okay? And on a similar set of parallel plate capacitor, I want to look at the case that we have this dielectric slab inside the plate, and now we are trying to slowly slide it out of the plate, okay? What I want to see is that I want to look at what energy, what force you may experience as you take the slab out of the plate, okay? So in what I'm gonna do next is basically the work energy theorem. I want to say that I'm taking this slab out of the capacitor, and as I do that, I'm doing some work, okay? And comparing how much work you're doing by the displacement, you can measure how much force you need to put in, okay? So let me get rid of most of these ones. I'm going to leave this on because I'm going to use them, okay?
Professor.
Yes.
So as you're removing the slab out of the capacitor, you are effectively reducing the charge of the capacitor, right?
Yes and no. And in fact, I want to consider a case that we charge it up and then we disconnect it from the battery because I want to work on a closed system, right?
Okay.
If you keep it connected, I'm going to discuss that as well. If you keep it connected, yes, you do some work, but battery can do some work as well. And of course, I'm going to look at that as well. That's very interesting.
Okay, good. Thank you.
Okay. Okay. So you know what? Let me draw something bigger and better. Okay, so imagine the green cube is a dielectric. Okay, and what we are doing is that we have this dielectric, we are pulling this out with the force F. imagine we have this a capacitor with the dimensions of length being L, the distance here being D, and the width here being W. Okay, so we have this capacitor, and this is the energy stored in the capacitor. Okay, so the situation here is this. What I want to do is that I want to connect the capacitor to a battery, okay, and then I charge it up. There will be some charges, positive and negative, on these two plates. Then I disconnect it from the battery, okay, and I start pulling this out. So I have a closed system, right? As I pull the slab out of the capacitor, I'm doing some work. At the same time, that work should change the energy stored in the capacitor, okay? So there is some work done by me. I want to say that is dW, which is the force that I'm exerting times dx. dx is how much I'm taking out, and F is the force, and dW is how much work is done by me, okay? At the same time, the work, the energy of the capacitor is 1/2 CV squared, okay? So in this case, I have charge, I disconnect it from the battery. As I take out, the V can change, okay? But what cannot change is the charge on the capacitor. So the better equation to calculate the energy of the capacitor in this case is actually 1/2 Q squared over C, okay? The two equations are equivalent when you know what is the V and what is the Q, but in this case, the V can change, so I'm going to follow this equation to calculate what is the energy of the capacitor, okay? So following this, okay, the force that I need to move this slab, should be negative of dW dx, okay? This is basically conservation of energy. And this dW is how much the energy of the capacitor changes, dx is how much I move that. Sounds good? So what is changing here, Q is constant. Q is not changing. Q is how much charge you have on the two plates of the capacitor. As you move the slab, what is changing is the capacitance. If you have the slab fully inserted, we calculated how much the capacitance it is. If we have a slab fully taken out, this is the case of the parallel capacitor without any dielectric, the parallel capacitor in vacuum. If you have partly dielectric and partly vacuum, capacitance can be calculated, and in fact, that's one of the problems I assigned to you for this week. Okay, so I don't want to calculate that step by step, but I can tell you the capacitance, okay, is epsilon naught W over D. And we have two terms for capacitance. One of them is epsilon R times L. The other one is negative of chi E times X. X is how much vacuum we have. L is the total length of the capacitor. And D is separation. The W here is the width. Okay, so L times W here is going to be the area. Okay. And basically what you want to do for that problem is that if you have a capacitor in this sort of configuration, half vacuum, half dielectric, you want to consider you have actually two capacitors in parallel. One of them being only vacuum with a specific area, let's say this area, which is X times W, and your second capacitor is something like this, with dielectric, with the area being L minus X times W. Okay, so in short, the C, the capacitance, is a function of X, how much it's out. So if you look at the energy, okay, the energy in terms of this is going to be a function of X. Okay, so
Professor?
to make that clear. C is a function of X. So here we have C as a function of X. That makes W a variable as a function of X. Yes.
In the capacitance equation, in the parentheses, is that X sub E times X, or?
This is chi E. This is the dielectric permittivity.
Okay, and is it that times X?
And that's times X. X is the distance here.
Okay, got it. Thank you.
Professor,
Yes.
I actually have a question. In this specific case, we actually have like the dielectric being taken out. Is there a way to solve for the, I guess you could say, the capacitance over time as the dielectric is removed from the capacitor?
Capacitance over time. So you want to consider a case that you're moving it with constant speed or something like that?
Yeah. So basically, you'd be removing the dielectric.
Yeah. So you could do, so as long as the capacitance is a function of X, that means if the location of the dielectric changes, capacitance changes. And depending how the location is changing, you can relate the capacitance to time or anything else.
Okay.
Yeah. But at this point, because we are specifically looking for the force, what matters is that how energy changes as a function of X, okay? So we don't want to include time here, because we want to find force, and for force, you want to look at the work per displacement. Sounds good? So let's take the derivative of this. Force is, again, writing this one is negative of dW over dx. And if this is a W, we get 1/2 Q squared over C2 dC over dx. Okay, so you have a negative sign that is here. And then we get a negative sign because we are taking the derivative with respect to C. Okay, and that is going to be, so one negative sign here with this negative sign cancels out, so we get 1 over Q2 over C2 times dC over dx. And this combination, Q2 over C2, is actually voltage to the power of 2. Okay, and we can write it in terms of 1/2 V2 dC over dx. Sounds good? And then dC over dx is negative epsilon naught. Sorry. Chi E W over D times F B negative of all right, so this is just mathematical derivation. Force is negative of dW over dx. And I just wrote that in a little more simplified way, 1/2 V squared dC over dx. And remember, this V potential is how much we actually, the potential we have across the parallel plate. So Q2 over C2 is V squared. And dc over dx, I just calculated this and put it back into the equation. So the force is negative epsilon naught chi e w over 2d. This w here is the width, d is separation, and v square is the potential to the power of 2. Okay, so again, what we did here, we charged up capacitor, we disconnected the battery so that the Q remains the same and constant, and we started pulling the slab out of that. What I calculated here is that how much the energy of the capacitor changes as a function of time. And knowing that it's a closed system, if the energy of the capacitor is changing, probably, not probably, of course, that energy should directly come from the work I am doing, taking the slab out, okay? And from that one, I measured the force. Force is negative, meaning that there's a force towards the positive x direction, trying to make x, makes x small to negative x direction, okay? So that means I pull it this way, but the slab prefers to stay inside, and that's the way the energy can be minimized. Sounds good? And another way you can look at this is if you keep it connected to the battery, okay? So in a way, the force at any moment you feel is not going to be different, okay? So what happens in this case, if you have a battery connected to this, is that now the system has 3 components. So one is the capacitor, one is me pulling the slab out, and the other one is the battery. So if you want to use the conservation of energy, we should include the work from all of them. Here, I just included the work from me, and then related that to how much the energy of the capacitor is going to change, okay? So I'm going to erase this one and quickly discuss what happens in that case, okay? So what I want to keep here is this. I want to say that when we looked at the closed system, the force following this equation from beginning to the end was 1/2 v square dc over dx. Okay, so I want to keep that there, but I want to erase the rest. Now, the subtle thing is that you can make a mistake but not including the work done by battery, okay? So if you keep the battery connected, you are keeping the voltage across the capacitor the same. So the W, you can write it in terms of 1/2 V CV square, okay? And if you follow this, and if you say the force is negative of dW, the change in the energy of capacitor over dx, what you find is that you take the derivative of this, and that becomes negative 1/2 CV square. And now, negative 1/2 dc over dx times v square. Because v itself is a constant, you're taking this derivative. What you end up having here is a negative 1/2 dc over dx v square. Okay, this is the mistake you can do if you forget to include the work done by the battery. What is mistake? If you look at this, looks very similar to this, except you have a negative sign here. Okay, and that's because the work done by battery is not included. If you include the work done by battery, what you need to include is this. Change in the energy of the capacitor has 2 components. One of them is the work done by me. I'm writing it at F me times dx. This is how much I work. And then battery does some work as well. And The way the battery works is that it can send more charges on the capacitor. So if the potential of the battery is V, it can send some more charges on the capacitor. So this is the correct conservation of energy when battery is connected. Okay, and if you look into that, if you write the force that a slab puts on me, F is going to be negative of dW over dx. Okay, so this is the change in the energy of the capacitor as the slab is moving, plus the potential is being constant, dq over dx. And this is how much work is done by the battery, okay, as we move the slab. If you combine these two, the first term is going to give us negative 1/2 VC square, okay, this is a negative 1/2 VC square, the term we had. Now, if you look at the second term, dq over dx times v, that's going to be v square dc over dx, because q itself is CV. Okay, the q itself is CV and v is constant, so v times this v becomes v square, and then dq dx becomes v times v dc over dx. Okay, and if you look at that, the combination 1/2 VC square. Okay, I did a mistake here. dW over dx is 1/2 V square dC over dx. Okay, so this is the first term here. And then we have v dq dx becomes v squared dc over dx. Combined, that becomes positive 1/2 v2 dc over dx. Okay, so now, once the correct conservation energy equation is written, we get the force becoming exactly similar what we expected and exactly similar thing that we found from the other approach. Positive 1/2 v squared dc over dx. Okay, so whether you keep the battery connected or not, at the end the force is going to be the same, but the way that you need to set up the conservation of energy equations are different. Sounds good? This is one of the examples in the book, by the way. I don't know which one, but if you look at the chapter of forces on electrostatics, this is the only example there. Any question? When the dielectric is removed, does that mean the orientation of the dipoles in the dielectric revert back to the original orientation? Yes, they go back to original orientation, and that means they're going to be randomly oriented in a way that there is no net polarization or anything, so chaotic. So there's no net polarization anywhere, no net charge, net polarization. Sounds good? Okay, guys, we are done. Okay, so we finished chapter 4 and we are done for the semester. Next Tuesday, we will have a quiz. So I'm planning to start the quiz early on in the class, so 9:30 in the morning. I'm gonna start the quiz. Once the quiz is done, I'm planning to give you the solution of the quiz, explain the solution on the board, and I hope that we have time to go over the solution for the midterm problems as well. If we did not get a chance to do the midterm here, I'm going to email you a PDF or picture with the solution of the midterm so that you can use that for preparing for the final exam. Sounds good? So reminder, you have homework to do Tuesday, and those problems are very carefully selected, okay? So try to do them, try to understand them, and as you work on those homework set, you're gonna learn a lot, okay? So don't try to go through them quickly. That's actually a learning process, going through them one by one. Okay? Thank you too. Okay, so see you guys on Tuesday. Work hard, stay focused, okay, and then you will be fine. So take the quiz as one first step for final exam preparation, and then the week after we have final exam. Good? All right. Enjoy the rest of your day. See you on Tuesday morning.